Greetings. My name is Ernesto Racheva. I'm a Master Science student at the National Autonomous University of Mexico at the Institute of Materials Research. And I did this work with my supervisor, Dr. Horacio Navarro Chavez, and we presented you the work titled Thus of Two Coupled Fibonacci Chains. So let's start. First and foremost, what is the density of states? Well, the density of states tells us the quantity of states that are squeezed into a certain value of energy. So, for example, the higher the energy, the density of states, for example, in this case and in this case, this means that there are a higher number of states at this value of energy, right? So what else? Also, atomic layer stacking is a reality nowadays, thanks to sputtering, deposition, and many other techniques. So in the sense that, so this problem is not like far from reality if we want to study it. Also, in high temperature superconductors is found in materials that are stacked. And an example of this is a material that you can find in the literature as YbCO. It's a compound of yttrium, barium, copper, and oxygen. And the structure of this material or this crystal is stacked. One of yttrium, another one of barium, and another one of copper oxide. Well, Fibonacci. What is Fibonacci? Fibonacci is a certain type of quasicrystal. And what are quasicrystals? Quasicrystals are materials with atomic order, but with forbidden fold symmetries and no translational symmetry. So a Fibonacci chain is a special type of quasicrystal because it shows no translational symmetry, but is an ordered structure. Also, a Fibonacci chain can be obtained by the same algorithm the respective number follows. That means it follows this formula and is the nth Fibonacci number. In this work, we study the symmetry of a Fibonacci chain. First, we study, sorry for this. Okay. First, we study the model of two coupled periodic chains, like, for example, the one shown in figure 1. And we compare it to the Fibonacci results. But we do this for two reasons. First, this model of two periodic chains coupled is the closest model to the models we're trying to solve. Also, this problem can be solved analytically. We show here the method. And once we know the results of this model, we can compare it to the Fibonacci case or to the Fibonacci situation, which is shown in the figure 2. And we can then explain what happens in the Fibonacci situation. So first, to solve the periodic situation, we propose an eigenfunction in this form. It's an eigenfunction that has two bases. And also, then we insert this expression in the Schrödinger equation that is given by this. And then we diagonalize. In which we get the following eigenstates, right? So we can see here like this. Well, this expression 2 beta cosine of Ka, it's the energy spectrum of a linear chain. So when we couple two linear chains, we got an extra term that is the absolute value of T that will serve as a gravity center. Yeah. So, well, here are the results. We did this calculation numerically in the sense that to compare the analytical results with the numerical ones. And what we get is the following. For example, with T equal to -1 and beta equal to -1, this is this case, the periodic one, we get that the linear chains are this one. Well, are these that I am going to show. So what we see is that this density or this part of the spectrum and this other one are the density of states of singular linear chains. And what we see is that they are centered, or the gravity center, it's at 1 and -1, as we see in the energy spectrum, right? So what happened if we change the value of T? What we see is that then the value of T is minus 0.5 and 0.5. And the linear chains, again, are this of the single linear chain and this one. And we can see that these densities are centered at minus 0.5 and 0.5, right? Let's erase this. So once we do this, we do the Fibonacci situation. And what we see is not like a very big difference from the periodic situation. Why? Because, well, these little gaps that are shown here are because of Fibonacci. Why? Because in some sense, the way the beta parameters are accommodated in the chain is in some way like random, but it's ordered. And if we remember the Paris distortion, we can see that these gaps are forming because of two different lattice hopping parameters, beta sub L and beta sub S. But what we see is that these both densities, this and this, are centered at -1 and 1, right? We choose two values for beta in a way to like simulate the periodic case. So, for example, this is not so far from the linear chain situation. What we see when we make this difference bigger is that the gaps are bigger, but the overall situation is the same, right? So, well, what we can conclude about all of this? Well, first, that thanks to the tight bindings Hamiltonian and the linear combination of atomic orbitals, we can solve exactly the problem of two coupled chains in the periodic situation. But this is not so far from, and in the Fibonacci situation, this is not so far from the periodic case. Well, we already see why, right? Well, to solve the Fibonacci chain, one can use quasi-periodic approximant or make the chain as long as one wants. And we will not see a lot of difference from the periodic situation, right? The density of states shows that the T parameter works as a gravity center for the individual chain spectra. This means that changing the distance between the two chains will change the edges of the band. Well, this is important because in some way we can see that the distance of two coupled chains will change the behavior of the system overall. So these results are useful to study electronic correlation in materials, which is a problem of many bodies. So so far we have got the basis to study the many body problem and to explain many systems. So thank you for your attention, and I'm open to questions. Bye.